The idea that we start with a single cell, even us.
It always fascinates me that something so complex could actually work.
I was always interested in how does everything actually work? How does nature actually work?
It's very easy for people to feel that we know so much about the biology of a cell that there's not much left that we could be modelling, and why would you bother?
We love to sort of think of it as an engineering problem.
What's really interesting, it's an old problem.
How can we describe the full complexity of a cell in meaningful mathematical models?
Having this groundbreaking ambition to build a whole cell model.
Yeah, the idea of being able to predict how an entire cell behaves is an incredible idea. I mean, that's the basis of MACSYS, right?
Yeah, MACSYS is a grand challenge.
I mean, it's an enormous challenge.
We were talking about a little bit like it's not so much a moon shot, but like a Mars shot.
Which, if it wasn't, you could argue it wouldn't be worthy of a center of excellence.
In fact, that's the scale of this challenge.
Understanding, the depth of what we're trying to achieve, the size of the task that how much we bit off, and watching people grapple, including myself, with how we're gonna chew it and digest it.
If we can't model a cell, we can't really predict how it works. We can't really predict what it will do in response to some sort of intervention.
Developing methods to query biology, to query the cell.
If we understand how a cell works, we can understand how it might not work.
And making these methods to be predictive so that you can use them as a tool, you can use them for discovery.
The advances in silico work, so modelling in computers, allows us to ask questions that we can't answer with biology.
Being able to understand and predict what is going to happen to a cell across different types of cells, really the applications will be quite limitless.
Medicine and survival are probably the critical thing when it comes to an individual's reason to why we might care about things like this.
It matters because most of the big problems we would want to solve, whether it's in biology and conservation biology, or the impact of climate change on biology, or the way in which some microbes can impact on human health.
So this includes biotechnology and in health.
For most of the understanding that we need to be able to predict what's going to happen, not just know what did happen.
All the biologists in MACSYS, myself included, when we first sort of came up against, what this is all about, the first reaction you have is just, how is that possible?
You only have to go to a biology seminar or hear a biologist talk before you get a sense of how complicated biological processes can be.
I love the complexity, I love all the detail.
Inside the cell, there are many different entities, dynamic entities.
And it's the sum of all those reactions happening together that influence each other that we're trying to nut out.
And I think that's where it's wonderful to have the foil of mathematics, which is all about minimalism.
Working with a theoretician can be confronting in that we often just want to know what the key processes are, and that can be frustrating.
Because as a biologist working with a mathematician, you're kind of like, well, what do you then... I go to the lab and I do experiments and I can bring that to you, but what are you doing? Talking about equations?
But it can also be liberating as well when hopefully everybody in the conversation realises that everyone's got the same goal.
So it's really interesting to bring together two disciplines, one which is all formula-based and very structured.
What's interesting about the complexity of the cell is that no one mathematical technique or approach is going to be enough to make these problems yield.
And then biology, which almost follows no rules.
And we need the support of scientific experts, molecular biologists, cell biologists.
I think it's more that we're able to do things that we've thought, oh, this would be really nice, but it's not worth doing.
When we have a model, we try and predict something within their experiment, and they can tell us, okay, that's correct.
But now that we have mathematicians involved, we can do these really hard, nuanced things.
Or they can tell us that, okay, that's totally wrong, in which case we can iterate with the model over time.
I find talking with experimentalists like the biologists, it really sort of turbocharges what you can find out, having a human who has an expertise in this area.
The solar system is so complex and we need lots of expertise from different disciplines.
There's a huge diversity of researchers across many different fields of biology, maths, computational science.
I've been impressed about how everyone's been been mucking in together, been getting on across the disciplines.
And each of those fields also is massively diverse.
I haven't worked with biologists before.
I've not worked with mathematicians before.
And it's something that's certainly very challenging in terms of being able to communicate.
It wasn't just that we didn't have a common language, it was that we had the same words that meant different things.
The words that we use in our disciplines are so entrenched.
Things like function, which has a very precise definition in biology and a very precise definition in mathematics, and it's not the same definition.
But we are learning, and I think that's what this centre is facilitating.
So we're educating each other, and that's a fascinating experience.
And now when these biology scientists talk about it, I think I do get 50 to 60% of it in the first go.
And I think what's really exciting about MACSYS is that we're jumping in to ask the bigger question of, okay, so how does a cell really work when we take into account everything that's going on?
And the timing of the centre is superb.
There's been these advances at the intersection of maths, computational biology and biology, where things have been achieved that just weren't possible 10 years ago. Like, they just seem like complete fantasy.
I think technically we are ready.
5 years ago might have been a little too soon. 5 years from now would definitely be too late.
Because we have the skills, the team that's coming together, we have the technical capability, both in a wet lab and dry lab setting, to bring to this really kind of challenging and diverse problem.
So for the first time, I think it's really possible to achieve this vision of having a predictive and fully computational model of a cell.
What we can do and what we can predict is going to have a huge step change with everyone working together like this.
It will be really powerful, and I think we're going to learn things that we couldn't learn any other way.
It's very exciting. It's basically what I always wanted to do, and now we're actually making a step in this direction.
A centre of this scale with this many people from all the different disciplines and this much time that we've all dedicated to this shared goal is, yeah, it's huge.
You feel like you're on your way to Mars, yeah?
We are on our way to Mars, big time. We are so on our way to Mars.